Hey everybody, Dr. Anna here, and we are continuing here with the origin and environments of sedimentary rocks. This is segment 4. In segment 3, we stop right here. What is the distribution of marine life is depending on? And remember, we said the temperature of the seawater, the salinity of the seawater, and the energy level of the seawater. So now we're going to look into all three of these things. So the temperature distribution of the seawater. The ocean temperature greatly impacts where the marine species can live. You probably know this. Species often have preferred temperature ranges, which determine their geographical distribution. And as temperature changes, they either die out or they have to be able to adapt different environments with different temperatures, which is better suit their needs. So I have a movie about the temperature variation, so let's watch it.
We're going to be talking about temperature variations with depth in our oceans. Now, the temperature variations that we see, these profiles, we see 3 different profiles, and they're all dependent on where you are located in the oceans, if you're in the low latitudes by the equator, if you're in our temperate zones, or if you're in our polar zones. And that's because the temperature variations that we see are all at the surface and are dependent upon those sea surface temperatures. So when we start to draw these out, we are going to draw a nice profile. And I'm going to put all 3 on the same scale so we can watch how that goes. So temperature is going to be on the top, and it will be in degrees Celsius. And we're going to go from 0, 5, 10, 20, and 25. Okay, and then our depth will be on our vertical axis in meters from 0. So the first place we're going to start and look at are going to be our polar areas. So the water in our polar regions are very cold. So if we think about the Earth and in the seasonal variation, as the Earth is orbiting around the sun. In the winter months, this area goes through periods of darkness. In the summer months, we're still kind of getting some sunlight, but it's not a lot to like warm everything up. So these are very cold areas. And we start to see our polar profile for our seawater. It looks something like this. So in the poles, let's see, I'll write this here, our polar area. We have cold water from the surface down to depth. So there's very little change in our polar regions. So these are places where there is no obvious thermocline, okay? And the water is cold from the top to the bottom. Down at depth, the temperatures we're looking at, you can think kind of 3 degrees Celsius, but deep water can range from anywhere from -1 to 3 degrees Celsius. So it's very cold down at depth as we get down there. Okay, the next one we're going to look at is the complete opposite, the extreme, which is going to be our tropical zone. And these are all converging at the same place. So this is our tropics, okay, or our low latitudes. And what we see here is that we have this really warm surface layer at the top. And then there's a zone towards the bottom, kind of right through here, where we have this rapid change in temperature with depth. So this has a very distinct thermocline, but the thermocline is low. And when you cross into this transition, it's going to go from being very warm surface water to very cold, deeper water. So it's a very distinct transition, and it's much deeper down. Right? And that's this warm, uniform layer is very nice, very tropical, and it's what we think when we think of our tropical areas. Now, our temperate latitudes are a little bit different. They're kind of between the two, and they're a place where we actually do see some seasonal variation. So I'll just draw an easy profile, but this kind of comes down. And again, they're all converging. So this is going to be our temperate. Okay, so these are places where we have seasonal variation. We have warmer water at the surface, but our thermocline, so this zone where we see this rapid change, it's much larger. So it has the thermocline starts more shallowy and it continues at a deeper depth. And we're going to see some seasonal variation. So The sea surface temperatures, because we're at these temperate latitudes and we get seasonal variation, it's going to change. And in the winter months, the thermocline will be less pronounced, and it's going to be more pronounced in the summer months. And that's because in those summer months, we get more of that incoming solar radiation. It leads to warmer sea surface temperatures, so it's going to vary, and that's what this dash is. And the thermocline in this area is thicker. It's a wider zone with the oceans. So those are the three profiles. You can see that overall they all converge down to really cold, deep water. This is all happening pretty, like the warmest areas in our oceans aren't super deep, so most of our seawater is very, very cold. And what's interesting, if we look at the oceans, the average ocean temperature of all the water is 3.9 degrees Celsius, which is cold. And this deep cold water, or this deeper water that's very cold, is bringing down this average temperature. So it takes away that really warm surface tropical water because there's not as much of it as there is in our deeper ocean. All right, so that's a big thing with temperature variations at depth. The one thing you want to remember is our thermocline. That's a good term to have. So the thermocline is a zone of rapidly changing temperature. Okay, so that would be the one term you want to take from this. And then just remember, in our polar areas, we don't see much change, so there's no obvious thermocline. In our tropics, we see a very significant change, and it's a smaller zone. So it's a smaller zone, but it's deep. But it does have a transition. And then our temperate areas, we do see seasonal variations in our thermocline, and it's going to be a much wider zone where we see that transition in temperature. I hope this helps you better understand how temperature varies with depth in our oceans.
So the second one is the salinity. And as you can see on this picture, in the ocean, we have a mixture of approximately 96.5% pure water. You can see here, these are the water molecules, and this is a sodium ion, and this is a chlorine ion. So both of them are surrounded by water molecules. So 96.5% by weight is the amount of pure water molecules, and 3.5% of salt, which is sodium chloride. And then there are some dissolved gases, some organic materials, and then some undissolved particles. The salinity of the seawater exhibits a low variation, and it's about 4% altogether. The world ocean, on an average, has 35.5 parts per thousand. So when you have no 0 underneath, it's called part per thousand. Okay, so 1 part in 1,000 parts. Now, what is the variation and how does it go? Is depend on the balance between evaporation. So you would have increased salinity in the tropical desert, where it would be decreased salinity in the rainforest, obviously. So it's the balance. It depends on the balance between evaporation and precipitation. And remember, we just went through the climate zone, so we know that at the tropical rainforest, there is a lot of water coming in, so the salinity goes down a little. Whereas the tropical desert, there is not much rain coming in, but there is evaporation, so therefore the salinity is going up. We have more sodium chloride because the water evaporates out, and the salt will not go with it. Graph shows the variation in ocean surface temperature and salinity. So on the y-axis, we got the temperature. You can see it's 3020. It's in degrees Celsius. And on the x-axis, we have the latitude, starting from the equator, going all the way to basically to the North Pole and the South Pole. So as you can see, as the temperature increasing, the amount of salt in the ocean is increasing as well, except in the tropical rainforest. Because what happens in the rainforest? In the rainforest, there is a lot of rain coming in, therefore it dilutes the water and you will have less salt relative to the amount of water. In the tropical desert areas, the salt is a little bit higher than other places, and that's because the water evaporates, therefore there is more salt relative to the amount of water. So the next one is the energy level, and you understand that it's also a limiting factor. For example, we already mentioned that at the shoreline, life is really bad because everything is changing. It's very, very high energy environment. The waves are coming, the tides are coming, So it's really, really hard to survive. Like if you're a clam, you really have to grow up very thick, very ugly. You have no energy for ornamentation. So only very, very certain type of plants and animals can live in these zones. And now we are finally going to start talking about the sedimentary environments. These are areas where the sediments can actually deposit. It can be distinguished from other areas on the basis of its physical, chemical, and biological characteristics. Before we can study the ancient environment, which is our goal in this semester, it is helpful to consider the types of sedimentary environments we have presently on Earth. These are the main types. We have the continental, transitional, and marine. So, continental, transitional, and marine. We kind of learn these environments in physical geology, but just a little bit. So, on the continent, we have to talk about the soil, the lakes, the glacial environment, and the fluvial, which is the river system or stream system. In the transitional environment, it's between continent and marine environment. We have to talk about deltas, the beach, the swamp. And then in the marine, which is always below the sea level, we have to talk about the continental shelf, the slope and the rise, and the pelagic means the abyssal plain environments. So this is just one picture showing you all these environments. You see the continental one. You can see the glaciers up here, the lakes, the stream, like the fluvial environments, and then the transitional environment, and then the marine environments. Let's start with the continental environment. The first thing we have to talk about the soil, paleo soil. If we have to recognize an old soil layer, what do we look for? Soil is the loose sediment forming on top of the rocks by weathering. How can we recognize ancient soil? We call them paleo soil. Sometimes it is difficult because diagenetic alteration. Remember, diagenesis is when the sediment becomes sedimentary rock by compaction, by chemical precipitation. We learned this in physical geology, so I just refer back to that. However, a lot of the times when there are roots, in the soil, you have roots and animal burrows. Those are very diagnostic features, and we can see them in the old soil layers as well. So it really helps us. However, this is important to understand. It's extremely hard to pick out paleo soil layers before we had plants and animals on the surface of the earth, on the continent. Life started in the ocean, so they long time before the plants and the animals actually came out to the land. So in those times, it's extremely hard to differentiate the paleo soil for just the normal regular marine rocks. This here is a cool picture showing you the soil environment, and you can see that the roots going all the way through the whole layer, and there are little burrows and other features also, which makes it easy to tell that this is a paleo soil. There's another one here. Now, the lake depositional environment. Lake sediments are relatively rare in the sedimentary record. However, they might be very important to recognize. Only way we can recognize this is the low diversity of fossil assemblies. I think this is the time when I ask you, what do you think? Where is it better to live in, salt water or fresh water? Just think about it for a minute. If you all think about the Smith Mountain Lake, we already mentioned that it has a very low diversity. So the truth is that it's much better to live in salt water for animals with salt water in them because they need freshwater environment. So it's really interesting to know. Now, the glacial environment, these are really, really cool. This is really, really important to know that it was a glacial environment because you want to see what kind of climate did we have during the Earth history. And seeing glaciers, that tells you that it was a cold climate at the time. Am I right? And with that, the glacier studies, we can actually tell that there were times when the Earth was extremely cold and glaciers could be formed even at the equator. Studying glaciers today is really very important as well because of the future climate. We want to be able to see what has happened during the Earth history so we can predict what's going to come.
A glacier begins to move when it cannot handle its own weight. This is called internal deformation. Due to the intense pressure of the glacier and the heat of the Earth, the bottom part of the glacier can melt. This meltwater acts as a lubricant, which enables the glacier to slide. This action is called basal sliding. Before a glacier travels through a valley, the valley has a V shape, possibly with a river at the bottom. The spurs, which are ridges out of the side of the main mountain ridge, are interlocking, causing the valley to wind. After a glacier goes through a V-shaped valley, it truncates or cuts off the spurs, causing the valley to take on a U shape. Glaciers can also combine. When a deeper glacier combines with a shallower one, the land below the shallower one becomes a hanging valley, a valley atop a cliff. But how do glaciers alter the terrain? How do they erode the ground? Abrasion is the rubbing of a glacier and the ground. This explains why striations, or large gouges on rock, occur. We can use this information to determine which way the glacier moved. Sapping is when water enters cracks and expands by 9%, causing rock to become dislodged. As the ice moves, it attaches itself to parts of the rock, dislodging it and ripping it away in a process called plucking. All of these pieces of rock and debris, called glacial till, are taken away. But where do they go? When a glacier moves, the glacial till tends to accumulate on the sides and at the front. When the glacier moves, a line of till is formed. These types of lines are moraine. A drumlin is essentially a cluster of gravel or rock with a gradual decline in the direction of the glacier. A crag and tail is a strong area of rock that the glacier could not erode, with a gradual decline of typical softer material from the area.
So this interesting movie, I just want to show you a typical U-shaped valley, which was formed by the ice, and this is a typical V-shaped valley, this Yellowstone National Park. And this is the very famous striation. So when in a region, the ice going through in the ice, we have those sediment pieces, and they are carving the underlying rock. So it's very important sign that there was a glacier there. And then, of course, most importantly, we will have the tillite. This is the present day forming tillite, and this is ancient tillite. The tillite basically is unsorted, very unsorted, polymiced breccia, because these rocks are just in the ice, so they are unable to click each other, so they will never be rounded. It's always going to be angular. So it will have every kind of rocks in it, whatever the glacier is coming from, whatever kind of rocks it moved through, that picks up all the different kind of rocks, and they are not going to be rounded. They will be angular, very, very immature, very, very unsorted, just like you see it right here. And then there are finer grain stuff as well. So you could see every kind of grain size in a glacier. As I say, very unsorted. Then you will find these classic glacial erratics, which are big, big, big rocks, which is at one time in the glacier, but when it melted, it just dropped it, and then nothing can move it anymore. Ice can move much bigger pieces of rocks than anything else. Then in between mountains, you will have a lot of glacial lake forming. And during the melting, the sediment comes into the glacial lake and settles down. This is one of the coolest formation of sediment, which a lot of scientists is studying, because it basically gives us a layered rock we call varv, which is exactly the same as the year rings in the trees. Let me show you a movie here.
Today, we are diving deep into the fascinating world of geology, specifically at these mysterious layers of sediment called glacial varves. Ever heard of them? Don't worry, most people haven't. But trust me, they're like tiny time capsules, whispering secrets about Earth's past. So, what exactly are these WAVs? Imagine, you are standing on the shore of a glacial lake, surrounded by towering ice sheets. As summer arrives, the ice melts, sending a rush of sediment-laden water into the lake. This coarse, sandy material settles quickly, forming a light-colored layer on the lake bed. But as winter takes hold, the meltwater slows down, allowing finer clay particles to sink and form a dark-colored layer above the sand. Each year, this cycle repeats, leaving behind a perfectly stacked record of seasons in the form of these light dark couplets. These are the WAVs. By counting them, we can literally count back the years, uncovering the age of the lake and even tracing past climate changes. It's like reading a natural calendar written in rock. But WAVs tell us more than just age. The thickness of each layer reveals information about how much meltwater there was. Thick WAVs whisper of warm summers, while thin ones hint at colder periods. Chemical analysis of the layers can even tell us about volcanic eruptions or changes in vegetation. It's like a detective story, where each layer provides a clue to Earth's ancient history.
I have a couple of pictures of WARF, and you can really see that this is like 1 year sediment. So when you have this lighter grain area, that's during the summer, and the dark area is during the winter. It's not only that there is missing sediment. What I mean is the glaciers are frozen, so there is no sediment coming in. It's also like algae growth in there. So you can really see when the summer was really long, because then the layer is thicker and the layer is thinner. Sometimes you have more than just a couple of short years when the glaciers didn't melt much, then the white layer is a little bit thinner and the black layer is probably thicker. I have clay-sized glass and this summer silt-sized glass. That's when the glacier melts and brings in the larger grain size sediment. And during the winter, it doesn't. It's mostly clay. And as I said, some low organic material. They have examined this. So there is some burrows here. Like you see, there's some living things have messed it up a little bit. But these are actually actual years. Look at this 79. 78 had a really thick, probably very cold, long winter, because there was no sediment coming in. So as I'm drawing it here, these are real years, look. And these are 3 different boreholes from different lakes, so they can actually correlate pretty good. Look, I can go and correlate the winter of 78, the winter of 79. So this is between 78, 79, that black layer. And then here is 79 winter and summer. That was a pretty short summer. And look at this winter. This was really long and cold. There was a low warm up right here. So you see, it's amazing how much stuff can we read out of this. Look at 1981. This was a very long, very good summer, and the winter was relatively short. And then the 82 is really a warm summer again, and winter is very short. So these are amazing time capsules, and as you heard it in the movie, because look, you can learn a whole lot of, just like the earrings in the trees. Okay, I don't really want to go into this next one. I'm going to finish this segment right here, and I will see you in the next segment. Okay? Bye.